The blueprints for a high-voltage AC transmission system may appear to be just numbers and symbols on a piece of paper. But the linemen who actually put the system together must follow these plans exactly. Conductor sizes and materials, structure heights, line spacing, and devices such as spacers and corona rings that are added to transmission lines are all included in the plans of a transmission system for specific reasons. In this program, we're going to take some time to look at some of the factors that influence transmission system design. Now, knowing these factors will help you understand why it's so important to follow design drawings exactly when you work on transmission systems. Power systems are designed to operate as efficiently as possible. One of the most important factors considered in transmission system design is minimizing the possibility of power loss. Now, power loss can be defined as electrical power that is produced but not used productively. Power can be lost or wasted in many different ways. One of the main ways power is lost in transmission lines is in the form of heat due to conductor resistance. When design engineers plan out a transmission system, they know where and why power losses are most likely to occur, and also know what can be done to keep those losses to a minimum. They start with information about the power available and the power required. They look at the factors that determine the amount of power and power loss in the system, such as transmission voltages, conductor size and material, and the possible arrangements of a variety of structures. They determine how all these things will affect the power transmitted and received, and consider their design options. After selecting the best option, the designer can adjust the design to ensure the most efficient construction, maintenance, and power transmission possible with a minimal amount of power loss. In your job, you'll mainly be required to follow design diagrams to replace and repair parts of transmission systems. But sometimes, a specific part that's called for in a design diagram may not be available, and you may have to decide what part to substitute. The decision you make could cause a change in the characteristics of the system, a change that might affect power loss. It's important for you to understand what factors influence design characteristics and how those characteristics can change so you can make the right decisions to keep power loss to a minimum and maintain an efficient transmission system. The design of any electrical system is based on several easy theories that are commonly expressed as mathematical equations. Let's look at these equations and see how they apply to transmission system design. The more familiar you become with them and their applications to transmission systems, the better understanding you'll have of what's required of you in your job. The first theory we'll discuss is Ohm's law. Now, Ohm's law basically states that the current in a circuit is directly proportional to the applied voltage and inversely proportional to the circuit resistance. This means that if resistance is held constant while the voltage in a circuit is increased, current will also increase. On the other hand, if voltage is held constant while resistance is increased, current will decrease. The equation used to express Ohm's law looks like this. I equals E over R, where I represents current in amperes, E represents voltage in volts, and R represents resistance in ohms. In this form, the equation can be used to calculate current in a circuit when voltage and resistance are known. But let's look at another case. What if current and resistance in the circuit are known and voltage is what you're looking for? Well, the equation can then be rearranged to E equals I times R and solved for voltage. The Ohm's law equation can be arranged to solve for current, voltage, or resistance. Keep this in mind as we look at another equation that's used in electrical theory to determine the power in a circuit. The equation looks like this. Power, measured in watts, represented by P, is equal to voltage times current. Now, power can also be expressed by another equation. In this equation, the arrangement of Ohm's law that solves for voltage is substituted for E in the first power equation. Using this arrangement of Ohm's law, we can substitute the expression IR for E and get P equals IR times I. The equation is shortened to P equals I squared R. Since this equation includes current and resistance, it can be used to determine the power that's wasted or lost in a circuit due to resistance. For this reason, you'll often hear power losses called I squared R losses. These two power equations can be used together to show how changes in circuit design can affect power losses. In a minute, we'll see how these equations can be used to show that power loss in a transmission system is lower when the voltage is higher. Actually, there are many causes of power loss. We'll talk about some more of the causes later. But right now, we're going to look at two hypothetical transmission systems. We'll assume that the only power loss in both of the systems we'll see is due to the resistance of the conductors in each transmission line. Like most transmission lines, ours will be strung in 3 phases. But for this example, we'll look at just one phase of each system as if it were a single separate circuit. Then we can simplify the power calculations and still discuss the basic relationships between current, voltage, resistance, and power. Okay, let's get started. This illustration represents our 2 transmission systems. Each power plant generates 150 megawatts of power. Keep in mind that the power in each phase actually varies all the time. However, for simplicity, we'll consider one specific point in time when the power in each phase is 50 megawatts. Both systems run for 50 miles, and each phase has a resistance of 0.1 ohm per mile, which totals 5 ohms of resistance per phase. Now, let's say that one system has an applied voltage of 250 kilovolts, and the other one has an applied voltage of 500 kilovolts. By using the equation P equals I squared R, we can determine the power loss for each system. For each system, we already know the voltage, 250 kilovolts and 500 kilovolts, the power, 50 megawatts, and the resistance, 5 ohms. So in order to determine the power loss for either system, we first need to find the current. Let's find the current for the 250 kilovolt system first. We'll use the power equation, P equals E times I, and rearrange it to solve for current. I equals P divided by E. Substituting the known values for voltage and power, the equation reads I equals 50 megawatts divided by 250 kilovolts. This equation can't be solved unless the prefixes for power and voltage are the same. So the next step is to change the units of power from megawatts to kilowatts. 1 megawatt equals 1,000 kilowatts. So I equals 50,000 kilowatts divided by 250 kilovolts. Working out the division leaves I equal to 200 amps. Now this current value can be used in the equation P equals I squared R, and power loss due to line resistance can be calculated. Substituting the values for current and resistance, the equation reads P equals the quantity 200 squared times 5. Squaring 200 gives us 40,000 times 5. 40,000 times 5 equals 200,000 watts. This can be converted to 0.2 megawatts of power loss in the 50-mile line. The net power at the distribution station can be determined by taking the power transmitted and subtracting the power loss. So if the power in the phase is 50 megawatts and there's a power loss of 0.2 megawatts, the distribution station receives 49.8 megawatts of power. Now let's calculate the power loss for the system that transmits at 500 kilovolts. Again, the first thing to do is find the transmission current using the power equation I equals P divided by E. Substituting the power and voltage values for this system, we have I equals 50 megawatts divided by 500 kilovolts. Next, the units of power are changed from megawatts to kilowatts, giving us 50,000 kilowatts divided by 500 kilovolts. 50,000 kilowatts divided by 500 kilovolts equals 100 amps. Now the current can be used in the equation P equals I squared R to determine the power loss for this system. This time, the equation reads P equals the quantity 100 squared times 5 ohms. Squaring 100 gives us 10,000 times 5, which is 50,000 watts, or 0.05 megawatts of power loss. Now, taking the power transmitted and subtracting the power loss as before, we get the net power at the distribution station. 50 megawatts of transmitted power minus a power loss of 0.05 megawatts equals a net power of 49.95 megawatts. Let's compare the power losses of the two transmission systems and the power received by the distribution station. The 250 kilovolt system has a 0.2 megawatt power loss, allowing 49.8 megawatts to arrive at the distribution station. And the 500 kilovolt system has a 0.05 megawatt power loss, allowing 49.95 megawatts to arrive at the distribution station. Notice that with two systems that are exactly the same, except for line voltage, the system with the higher voltage has a significantly lower amount of power loss. Power transmitted at 250 kilovolts experienced a power loss of 0.2 megawatts, or 200,000 watts, while power transmitted at 500 kilovolts only had a power loss of 0.05 megawatts, or 50,000 watts. Transmitting at the higher voltage saved 150,000 watts of power. Now, you should keep in mind that the amount of power transmitted from any plant is determined by demand. If, for example, 50 megawatts are demanded at a line voltage of 250 kilovolts and line losses are 0.2 megawatts, the plant must generate 50.2 megawatts of power. The point of minimizing line loss is to reduce the amount of additional power that must be generated to meet distribution demands. We've just looked at some of the basic equations for electrical system design, and we've used the Ohm's law equations and the power equations in an example to calculate power loss in two transmission systems. We've also used those equations to show that relatively higher transmission voltages lead to lower power losses. During the rest of this program, we'll take a look at some other factors that are taken into consideration when a transmission system is designed. We'll see how these factors influence design decisions in order to build the most efficient systems possible. So far in this program, we've used some equations of electrical theory to calculate power loss in two transmission systems. From those calculations, we've seen how relatively higher voltages lead to lower power loss. The transmission systems we used in that example were purely resistive circuits. That is, the only opposition to current flow was caused by resistance. However, in any AC circuit, it's very rare that the opposition offered to current flow is totally caused by resistance. The total opposition offered to current flow in AC circuits is referred to as impedance. Now, impedance is a combination of resistance, inductive reactance, and capacitive reactance. Inductive reactance is the opposition to changes in current flow caused by inductance. Inductance is induced voltage that opposes changes in current flow. Capacitive reactance is the opposition to changes in voltage caused by capacitance. Capacitance is an electrical property of AC circuits that opposes changes in voltage. Since impedance is the total opposition offered to the flow of alternating current, its properties are major contributors to power loss in transmission systems. As an equation, impedance can be expressed like this. Z equals the square root of R squared plus the difference between X sub L and X sub C squared. Z represents the total impedance measured in ohms. R is resistance, also measured in ohms. X sub L represents inductive reactance, also in ohms. And X sub C is capacitive reactance, again in ohms. This equation can be used to illustrate some of the factors that contribute to power loss. Understanding these factors will help you make the best decisions for repairing the systems you work on while maintaining minimum levels of power loss. So, we'll examine each property contributing to impedance and see how each relates to transmission lines. Then, we'll take a look at how they all contribute to the impedance of a circuit. First, we'll consider inductive reactance. Now, inductive reactance is caused by inductance. Inductance is the induced voltage in AC circuits that opposes changes in current flow. The development of inductance is called induction. For example, this illustration shows a conductor that has an applied voltage and an alternating current flow. The current flow creates a magnetic field that expands and collapses around the conductor. The relative motion between the conductor and the magnetic field caused by the expanding and collapsing induces a voltage in the conductor. This induced voltage is opposite in polarity to the applied voltage. The induced voltage opposes changes in current flow because it tends to cancel the effects of the applied voltage. We can see how induction develops in a transmission line if we look at it as a loop of wire that runs from a power source through a load and then back to the power source. The current through the transmission line sets up a magnetic field similar to that set up by a one-turn coil. Transmission lines generally experience two types of induction: self-induction and mutual induction. When the magnetic field around a conductor builds up and collapses on the conductor itself, the relative motion necessary to induce a voltage in that conductor is created. This is referred to as self-induction. When the magnetic field builds up and collapses across another conductor, the relative motion necessary to induce a voltage in the second conductor is created. This is mutual induction. It's important to be aware of the possibility of mutual induction when you're working on transmission lines, especially when you're working on a de-energized line. You must always be sure to ground the circuit in the area you're working, because energized conductors will induce a voltage in de-energized conductors. Grounding the de-energized circuit directs the induced voltage to ground, protecting you from injury while you work. The amount of inductance in a conductor is measured in units called henries. The amount of inductance in a transmission line is determined by the length of the line, the distance between conductors, and the size of the conductors. An equation that's commonly used to calculate the amount of inductance in a coil can also be used to calculate the inductance in a transmission line. This equation explains inductance in terms of the physical properties of a conductor. L equals 0.4 times pi times n squared times A times mu divided by lowercase l. In this equation, L represents inductance in henries. 0.4 is a constant. Pi is also a constant. It has a value of about 3.14. N is the number of turns or loops in the coil. A represents the cross-sectional area of the wire. Mu is the magnetic permeability of the core. In a transmission line, the core is air, because air is what fills the space between conductors. Air has a magnetic permeability of 1, and the lowercase l is the length of the wire. Now, as we've seen, it's inductive reactance, not inductance itself, that makes up part of the impedance formula and therefore has an effect on power loss. Inductive reactance is the opposition to changes in current flow of AC, or pulsating DC, caused by inductance. Inductive reactance can be expressed in terms of the equation X sub L equals 2 times pi times F times L. X sub L, which represents inductive reactance, is measured in ohms. Pi, again, is a constant of about 3.14. F represents frequency, measured in hertz, and L represents inductance, measured in henries. 2 pi is not a variable. Frequency isn't a variable either, because the frequency of most transmission systems in the United States is regulated to 60 hertz. The only design consideration an engineer can manipulate when controlling inductive reactance is inductance. It's the only variable value left in the equation. Since inductive reactance can contribute to power loss, controlling the inductive reactance in a transmission line can help minimize power loss. One factor a designer can use to control inductance in a transmission line is spacing. In a transmission system, spacing refers to the physical relationship of phases to each other and to the relationship between conductors. Transmission lines must be designed to prevent phases from touching one another, resulting in phase-to-phase faults. However, the closer phases are to each other, the less the net effect of mutual and self-induction. The farther the phases are separated from each other, the greater the net effect of self and mutual induction, and, consequently, the greater the power loss. Now, the reason for this is that mutual induction has a greater effect than self-induction when lines are closer together. Mutual induction tends to cancel some of the effects of self-induction, thereby reducing the total effect of induction. On the other hand, when lines are relatively farther apart, self-induction in any one conductor isn't weakened by mutual induction. So, a designer, while making sure that lines aren't close enough to each other to allow phase-to-phase faults, places lines close enough to each other to obtain the most benefit in minimizing power loss. It's important for you to ensure that inductance is maintained at design levels when you're working on a transmission line. If inductance varies from design specifications, impedance may increase, which may lead to an increase in power loss. One thing you can do to maintain inductance at design specifications is to use proper clamps on transmission lines. Clamps are the devices that connect two conductors together. You have to use clamps that are the right size to maintain the proper cross-sectional area of the conductor. As we've seen, the size or cross-sectional area of a conductor is one of the factors that determine inductance. A clamp that's too small will decrease the cross-sectional area and cause the inductance in the conductor to decrease. However, a small clamp could also lead to overheating of the conductor, a very dangerous condition. A clamp that's too large will increase the cross-sectional area and cause inductance to increase. This could lead to an increase in inductive reactance, impedance, and power loss. If you're on the job and the correct size clamp isn't available, it's generally better to use a larger clamp than a smaller clamp, because the dangers of overheating could be more serious than an increase in inductance. If you don't make installations correctly, using the proper equipment and following the correct procedures, you might alter the orientation of magnetic fields and change the amount of self-induction and mutual induction in the line. Although separate incidents may not significantly affect the overall power in the transmission line, many inaccuracies can cause a cumulative change in power loss. We've talked about one way a design engineer can control inductance and thereby inductive reactance. And we've seen one thing you can do to help maintain design levels of inductive reactance in the lines you work on. Now, let's calculate the inductive reactance for a hypothetical transmission line so that later we can see how the inductive reactance of the line contributes to the circuit's impedance and thereby affects power loss. This illustration represents a transmission line with three phases that are close to each other. The line runs for 25 miles. To simplify this example, we'll calculate the inductive reactance developed in only one phase of the transmission line. The first thing to do is determine the inductance in the line. In this example, we'll assume that 1 millihenry of inductance is produced per mile of line. Since the transmission line is 25 miles long, the inductance for the phase is 25 millihenries. Now we can solve the equation for inductive reactance. X sub L equals 2 pi times F times L. Substituting in the values, the equation now reads X sub L equals 2 times 3.14, or 6.28, times frequency, 60 hertz, times inductance, 25 millihenries, or 0.025 henries. Multiplying these values, we find that X sub L equals 9.42 ohms. So the total inductive reactance of this 25-mile-long conductor is 9.42 ohms. In the last part of this program, we'll see how the inductive reactance in the line we've just seen contributes to the impedance in the line. For now, review the material in your text on inductance and inductive reactance. In the next part of this program, we'll take a look at capacitance and capacitive reactance. In the last part of this program, we discussed inductance and inductive reactance. We talked about what causes inductance and inductive reactance in transmission lines. We also saw what factors influence inductive reactance in a transmission line, and we used an equation to calculate the inductive reactance in one phase of a transmission line. In this portion of the program, we'll examine another property of impedance, capacitive reactance. We'll see how capacitance and capacitive reactance develop and what factors influence capacitive reactance in transmission lines. We'll also use an equation to calculate the capacitive reactance in one phase of the transmission line, which we used in the last part of this program. Later, we'll see how inductive reactance, capacitive reactance, and resistance combine to make up the impedance of the line. Capacitance is the electrical property of AC circuits that opposes a change in voltage. Capacitance is developed by a capacitor. A capacitor is a device that has the ability to store a charge. It consists of two plates and a dielectric. When a voltage is applied to the plates of a capacitor, the plates become charged to the voltage applied. The dielectric between the plates is an insulating material. It prevents the flow of electrons between the plates, allowing the plates to store the charge. This charge on the plates will remain until the voltage begins to drop below the value of the charge. In an AC circuit, when the voltage changes direction, the capacitor discharges. Conductors that are in close proximity to each other, such as a transmission line strung in phases, develop capacitance because the conductors act like plates in a capacitor. To understand how capacitance develops in a transmission line, let's look at just two phases that extend from a power source. Picture each phase as a plate of a capacitor. The phases are separated by an airspace, which acts as a dielectric. The voltages on each phase are different from each other at any one time. In other words, there's a potential difference between the two phases. The potential difference establishes an electrostatic charge between the two phases, as if the transmission line were a large capacitor. The amount of capacitance developed by a capacitor is measured in units called farads. The physical characteristics of a capacitor influence the amount of capacitance it develops. Those characteristics are the plate area, the distance between the plates, and the dielectric material. Basically, the larger the plate area, the greater the capacitance. The closer the plates are to each other, the greater the capacitance. And any type of dielectric has a specific value that contributes to the amount of capacitance. In a transmission line, the amount of capacitance is determined by the length of the line, the size of the conductors, the distance between the conductors, and the dielectric material, which is air. There's an equation that's commonly used to find the capacitance of a capacitor, or in this case, a transmission line. Again, like inductance, the equation expresses capacitance in terms of the physical properties of the conductors. The equation is C equals A times K divided by a lowercase d. C represents capacitance in farads. A is the area of the plates. K is a constant determined by the dielectric material. And D is the distance between the plates, or the thickness of the dielectric. In the same way that inductive reactance, not inductance, makes up part of the impedance equation, capacitive reactance, not capacitance itself, makes up part of the impedance equation and has an effect on power loss. Capacitive reactance is the opposition to changes in voltage of AC or pulsating DC caused by capacitance. Capacitive reactance is generally expressed in equation form as X sub C equals 1 divided by 2 times pi times F times C. X sub C represents the amount of capacitive reactance measured in ohms. Again, pi is a constant of about 3.14. F is frequency, a constant of 60 hertz, and C is capacitance, measured in farads. The only design factor an engineer can control when determining the capacitive reactance of a transmission line is capacitance, because it's the only variable value in the equation. From the equation, we can tell that if capacitance is increased, capacitive reactance is decreased. So if a designer makes a change that increases the capacitance of a line, he's actually decreasing the capacitive reactance. As we've seen, there are several factors that determine the amount of capacitance of a transmission line. Now, the designer doesn't really have control over the length of the line, but he can determine the spacing of the conductors and the size of the conductors to affect capacitance and capacitive reactance. For example, if the designer decreases the space between the conductors, the capacitance increases and the capacitive reactance decreases. In addition, increasing the sizes of the conductors is like increasing the plate area of a capacitor. If the size is increased, the capacitance will increase and the capacitive reactance will decrease slightly. The only factor a lineman can affect to change the capacitance of a transmission line is spacing. For example, let's say you had to replace a damaged insulator or stack on a transmission line. If you used a different insulator from the one in the plans, you could change the design configuration of the line by decreasing or increasing spacing. This would cause capacitance to increase or decrease from design specifications. Once again, separate incidents like this may not critically alter the overall amount of power loss in the system, but if they are repeated down the line, they could cause a cumulative change in transmission power. Now that we've seen how capacitance and capacitive reactance are determined in transmission lines and what factors can affect them, let's calculate the capacitive reactance of the transmission line we used as an example in the last part of this program. Later, we'll see how the capacitive reactance relates to the inductive reactance we already calculated, and to resistance to determine the impedance of the line and thereby affect power loss. Again, we'll use the same transmission line we saw before and calculate the capacitive reactance of one phase. First, the capacitance is determined. In this example, we'll assume that 0.5 microfarads of capacitance are produced per mile. 0.5 microfarads times 25 miles equals 12.5 microfarads of capacitance for the phase. Now we can calculate the capacitive reactance for this phase. Again, the formula for capacitive reactance is X sub C equals 1 divided by 2 pi times F times C. Substituting the known values into the equation, we get X sub C equals 1 divided by the quantity 2 pi, 2 times 3.14, or 6.28, times frequency, 60 hertz, times capacitance, 12.5 microfarads. Multiplying the values out, we find that X sub C equals 1 over 0.00471. Working through the division, we see that X sub C equals 212.3 ohms. So the capacitive reactance of the 25-mile transmission line is about 212 ohms. Later, we'll see how the capacitive reactance contributes to impedance and power loss. Well, now we've looked at two properties of impedance. We've seen how they develop and how they are determined, and we've looked at some of the ways you can maintain those properties at design levels. In the next part of the program, we'll look at the last part of the impedance formula, resistance, and we'll also see how that contributes to the overall impedance of transmission lines. For now, review the material in your text on capacitance and capacitive reactance and answer the questions at the end of that section. Up to this point in our examination of the properties of impedance, we've covered inductive reactance and capacitive reactance. We've seen how they're developed and determined in transmission lines, and we've calculated the inductive reactance and the capacitive reactance for one phase of a transmission line. The only part of the impedance equation we haven't looked at yet is resistance. Resistance is the opposition to current flow within a conductor. The amount of resistance a conductor has is determined by factors such as the conductor's length, the material that it's made of, and its size. As we saw in the discussion on power loss in the beginning of this program, resistance plays a direct role in power loss. We use the equations I equals P divided by E and P equals I squared R to see how changes in voltage influenced power loss when the resistance of a conductor remained the same. In that example, we looked at a transmission line that had a resistance of 0.1 ohm per mile and was 50 miles long. So the conductor's resistance was 5 ohms. Our calculation showed that if transmission power was 50 megawatts and transmission voltage was 500 kilovolts, current through the transmission line was 100 amps. Then we calculated the power loss, substituting the values for current and resistance. We found that for the 50-mile-long transmission line, there was 0.05 megawatts of power loss. Now, let's look at a similar example, but this time we'll see what happens when one of the factors that influences conductor resistance is different. For this example, we'll use the same amount of transmission power, 50 megawatts, and the same amount of transmission voltage, 500 kilovolts, which results in 100 amps of line current. We'll still say the conductor has a resistance of 0.1 ohm per mile, but this time we'll look at a transmission line that only runs for 25 miles, half the length of the one in the previous example. Even though the designer doesn't have control over the length of the transmission line, the length still affects the line's resistance. For example, 0.1 ohm times 25 miles results in a total resistance of 2.5 ohms. So a transmission line that is 25 miles in length has half as much resistance as the same line that runs 50 miles. Now let's see what this means in terms of power loss. Remember that the 50-mile-long conductor has a power loss of 0.05 megawatts. If we use the formula P equals I squared R to calculate the power loss for the 25-mile-long conductor, we find that line has a power loss of 25,000 watts, or 0.025 megawatts. From this calculation, we can conclude that the shorter the conductor, the less power loss due to resistance. Conversely, the longer the conductor, the greater the power loss due to resistance. But as I pointed out earlier, resistance is determined by the material the conductor is made of and the size of the conductor as well as its length. So let's look at conductor materials and then conductor sizes and see how they influence conductor resistance. Depending on the material used in the construction of a transmission line, its conductivity varies. Now, conductivity is the ease with which a substance allows current to flow. The greater the conductivity of a material, the less its resistance to current flow. In transmission and distribution, there are two materials commonly used in the construction of conductors. They are copper and aluminum. Copper is a commonly used line conductor because it conducts current very easily. Aluminum is widely used for transmission and distribution line conductors. However, it's not as conductive as copper. Even though aluminum is not as conductive as copper, it is lighter and lower in cost, which accounts for its wide use. For an aluminum conductor to carry the same amount of current as a given size copper conductor, it must have a larger diameter. A larger diameter results in a lower resistance, which reduces power loss. A rule of thumb that can be used when replacing copper with aluminum is that an aluminum conductor is selected 2 sizes larger than a copper conductor for the same job. Aluminum isn't as strong as copper, so in order to substitute aluminum for copper, aluminum conductors are often manufactured with steel reinforcing strands in the middle to increase the overall strength of the conductor. A conductor like this is called an aluminum conductor steel reinforced, or ACSR. ACSRs are the most widely used conductors in transmission and distribution. The last factor that influences the resistance of a conductor is its size. In general, the larger the wire, the lower the resistance. Wires and conductors are usually sized in units called circular mils, which is usually abbreviated cm. A mil is 1/1000th of an inch. In other words, there are 1,000 mils in an inch. A circular mil is a circle that has a diameter of 1 mil. Conductors in transmission lines may run 3 million circular mils or larger. Larger conductors, like those used in transmission systems, experience a phenomenon known as skin effect. Skin effect causes the flow of alternating current to concentrate in the outer surface of the conductor. This results in an increased resistance to the flow of AC in larger conductors. For example, here are 2 conductors of different sizes. Conductor A is 250,000 circular mils and has an AC carrying capacity of 405 amps. Conductor B is 500,000 circular mils, twice as large as conductor A, and has an AC current carrying capacity of only 635 amps. Skin effect can be reduced to decrease the overall resistance and increase the AC current capacity of conductors by grouping conductors in bundles. Conductor bundles usually consist of 2 to 4 small conductors that make up one phase and are tied together electrically, but separated from each other physically. For example, conductor C is 750,000 circular mils and has an AC carrying capacity or rating of 825 amps. If 3 A conductors are strung in parallel as a bundle, totaling 750,000 circular mils, the AC current rating is increased to 1,215 amps, a current rating that's greater than the current rating for one conductor of the same circular mil area. The higher ampere rating is due to the fact that resistors in parallel offer less resistance than resistors in series. Increased current rating is one of the advantages of conductor bundling. Also, because bundling counteracts the increased resistance caused by skin effect, The amount of power loss in transmission lines is also reduced by using bundles. So, we've seen that using conductor bundles can reduce AC resistance caused by skin effect. We've also seen how the material that a conductor is made of affects its resistance, and how conductor length affects resistance. In your job, be sure to follow the specific procedures for repairing transmission lines, replacing or installing connectors, and making splices. Improper procedures could lead to a high resistance connection on connectors and splices. This will increase the resistance within the transmission line and also increase power loss. Now, we've gone through all the properties that make up impedance. Next, we'll discuss impedance in more detail and see how the three properties, resistance, inductive reactance, and capacitive reactance, interrelate. And we'll also discuss two other factors related to power loss. But now is a good time to review the section of your text that covers resistance. Ask your instructor to help with any questions you have. Resistance, inductive reactance, and capacitive reactance. We've covered all the factors that make up impedance. We've seen how each of these factors develops and is determined, and how individually they affect transmission systems. In this part of the program, we'll see how these factors contribute to the total opposition offered to the flow of alternating current, that is, impedance. Now, in DC circuits, the only opposition offered to current flow is due to resistance. However, unlike DC circuits, AC circuits are subject to another source of opposition to current, that is, reactance. We've discussed the two types of reactance that affect AC circuits, inductive reactance and capacitive reactance. Resistance, inductive reactance, and capacitive reactance cause a special relationship to develop between voltage and current in AC circuits. This is a time relationship called phase angle, in which current either lags or leads voltage. Phase angle is a measure of the degree to which current lags or leads voltage. The relationship between resistance, inductive reactance, capacitive reactance, current, and voltage can best be shown by using vectors. A vector is a quantity with a direction. This illustration shows the vector relationship between current, voltage, and resistance. This vector line shows that current and voltage are in phase in a purely resistive circuit. That is, resistance has a phase angle of 0 degrees and current does not lag or lead voltage at all. This vector line shows that inductive reactance is 90 degrees out of phase with resistance. That is, inductive reactance has a phase angle of 90 degrees. In a purely inductive circuit, inductive reactance causes current to lag voltage by 90 degrees. This vector line shows that capacitive reactance is also 90 degrees out of phase with resistance. However, the direction of the phase angle is opposite to the direction of the phase angle for inductive reactance. So, in a purely capacitive circuit, capacitive reactance causes current to lead voltage by 90 degrees. To determine the total opposition to current flow in an AC circuit, the vector quantities are added, resulting in a phase angle that is greater than 0, but less than 90 degrees. Since inductive reactance and capacitive reactance are 180 degrees from each other, they are considered to have an opposite effect on each other. Because they are directly opposite vectors, the difference between the two is the resultant effect of reactance in AC circuits. That's why one is subtracted from the other in the impedance equation. It's important to realize that even though the equation states x sub L minus x sub C, the smaller value is always subtracted from the larger value. So if x sub L and x sub C have the same value, they cancel each other out, and the impedance of the circuit is due only to the resistance of the circuit. For example, let's say R is equal to 20 ohms. X sub L equals 10 ohms, and X sub C equals 10 ohms. 10 minus 10 is 0. 0 squared is 0. 20 squared equals 400. 400 plus 0 is 400. The square root of 400 is 20, so Z equals 20 ohms. In a situation like this, where inductive reactance and capacitive reactance are equal, the circuit is said to be in resonance. Transmission systems are not specifically designed to prevent resonance, but it's unusual to find a system in which inductive reactance and capacitive reactance actually are designed to have the same value. More common are systems like the 25-mile transmission line we've been using as an example in this program. In that system, we calculated inductive reactance and capacitive reactance that have different values. Let's see how inductive reactance, capacitive reactance, and resistance combine to make up the total impedance of that system. Our calculations showed that the inductive reactance was 9.42 ohms, using an inductance value of 1 millihenry per mile. Capacitive reactance was 212.3 ohms, using a capacitance value of 0.5 microfarads per mile. And resistance was 0.1 ohm per mile, or 2.5 ohms for the 25-mile run. To simplify the calculation, we'll round off the values for inductive reactance, capacitive reactance, and resistance. We'll round off X sub L to 9 ohms, X sub C to 212 ohms, and resistance to 3 ohms. Now, let's calculate the impedance of the line using the equation Z equals the square root of the quantity, R squared, plus the difference between X sub L and X sub C squared. And substituting in the values, the equation reads impedance equals the square root of 3 ohms squared plus the difference between 9 ohms and 212 ohms squared. Squaring 3, we get 9. 9 ohms minus 212 ohms is 203 ohms. Squaring 203, we get 41,209. Adding 9 and 41,209 gives us 41,218. The square root of 41,218 is 203.02, or about 203. So, in this 25-mile transmission system, there's an impedance of about 203 ohms. As we've said, impedance is one of the greatest contributors to power loss in transmission lines. To determine the power loss due to impedance, we can use the power equation P equals I squared R. Since impedance is the total opposition to current flow in an AC circuit, we can, in effect, substitute Z for R in the power equation and change it to P equals I squared Z. Assuming that this is a 500 kilowatt system with a current rating of 100 amps, we can calculate the power loss as power equals 100 squared times 203 ohms. 100 squared is 10,000. 10,000 times 203 equals 2,030,000. So the power loss is 2.03 megawatts for the 25-mile transmission line. Earlier, our power loss calculation for the line, which only took into account the loss due to resistance, was 0.025 megawatts. The total opposition to current flow offered by impedance for this same line is 2.03 megawatts. This is an increase in power loss of about 2 megawatts due to the contributions of inductive reactance and capacitive reactance. Now, we've seen that impedance in an AC circuit contributes to power loss in high-voltage transmission systems. We've examined the three elements that make up impedance in AC circuits and their effects on high-voltage conductors. We've also looked at some ways that systems can be designed to minimize power loss due to these elements. And we've seen some of the things that you can do in your job to make sure that the elements of impedance remain at design levels. If you understand how resistance, inductive reactance, and capacitance can change, you'll be able to make the most effective decisions if you have to make an adjustment that will vary their values in the lines that you work on. In this way, you'll be doing your part to keep power loss to a minimum in your systems. Another effect that contributes to power loss is called corona. Corona is the ionization of air surrounding a conductor at high potential, in which power is lost directly to the atmosphere. Corona results in an electrostatic field surrounding the conductor that creates power loss in the form of high voltage impulses, radio frequency interference, or RFI, television interference, or TVI, and audible noise. Under certain conditions, this field is visible as a blue glow. Detectable RFI and noise are good indications of power loss due to corona. The RFI resulting from corona can inhibit effective communication transmissions. So the effects of corona on radio frequencies are monitored and regulated to ensure that corona levels aren't high enough to cause significant RFI. If a lineman hears audible noise when making routine patrols of lines, he should be sure to report it to his supervisor, as this is an indication of RFI and power loss due to corona. In areas along the transmission line where there are sharp bends in the line or where conductors have been nicked or damaged, coronal loss is at its greatest. This is because current tends to flow along smooth lines. Sharp bends or nicks create areas where power can be lost into the atmosphere. Linemen can minimize corona loss by ensuring that conductors are handled properly so that sharp bends and nicks are prevented. Also, in areas where corona losses tend to be higher, devices called corona rings may be installed. Corona rings are connected directly to transmission lines and are supported by insulators at structures and other areas where there are bends in the lines. They provide a smooth surface, thereby limiting the effects of corona. Besides corona rings, another device called a static wire is connected to most structures. Static wires are used to dissipate the effects of lightning. They're tied directly to the tops of structures. Although static wires don't directly relate to power loss, they do prevent damage to transmission lines, which could otherwise lead to serious power loss. Static wires are strung overhead between structures, tying all structures together. They're also connected to a wire in the ground, called a counterpoise wire, that runs along the transmission path. The counterpoise wire also ties the system together and grounds it as well. Since lightning tends to be drawn to the highest point above ground, any lightning that would otherwise strike structures or transmission lines is generally attracted to a static wire. The resultant voltage surge is directed through the static wires to the counterpoise wire and is dissipated to ground, preventing damage to lines and structures. Well, we've gone over some of the major contributors to power loss in transmission lines. We've seen how voltage, resistance, inductive reactance, and capacitive reactance affect power loss and how they can be controlled to maintain a minimal amount of power loss in transmission systems. Even though most of the action against power loss is taken at the design stage, you are the last line of defense against power loss in the systems you work on. You must ensure that these systems are installed and maintained according to design specifications so that all the preventive measures established on the drawing board are effectively put into action on the line. This includes things like making proper installations according to design drawings and making good conductor connections to maintain reduced resistance and power loss. You should follow your company's procedures for crimping and cleaning conductor connections and splices. And you should always be sure to handle conductors with care. Avoid nicking, bending, and dragging conductors to help reduce corona effects. You should also be sure to install and replace devices such as corona rings and spacers in accordance with your company's specifications. By doing these things, you can help keep power loss to a minimum in your systems and ensure transmission lines that operate as close to design specifications as possible.